Good morning, students. Today in semiconducting materials, we will solve few problems. I am Dr. R. Priya, Professor of Physics, RMD Engineering College, Kavarapeta. Now read the question. Find the resistance of an intrinsic germanium rod of 1 centimeter long, 1 millimeter wide and 1 millimeter thick at 300 Kelvin. Assume Ni is equal to 2.5 into 10 power 19 per meter cube. Mu E is equal to 0.39 meter square volt power minus 1 second power minus 1. Mu H is equal to 0.19 meter square volt power minus 1 second power minus 1. So what is given in the problem is, first of all, the material is germanium and the intrinsic carrier concentration is given as Ni is equal to so much. Then mobility of electrons and holes are given as mu E is equal to so much and mu H is equal to so much. So what is asked in the problem is resistance, which means capital R. It is intrinsic, so Ri. So Ri is asked. So we know the basic formula for R is equal to rho L by A. So Ri is equal to rho L by A. Now I don't have rho here. Do I have conductivity? Okay. So I will rewrite the equation for conductivity. Ri is equal to L by sigma I into A. Then sigma I is known to me, that is Ni into E into mu E plus mu H. Now you see mu E, mu H, Ni, everything is given in the problem. So mu E is what? 0.39. Then mu H is 0.19. That is in the bracket. Then Ni is 2.5 into 10 power 19. That is given here. E is 1.6 into 10 power minus 19. So you find out sigma I. So I have the formula only to find out sigma I. I don't have directly a formula to find out rho, or if you want you can find out and then substitute here, no issues at all. This is easy, I felt, so I have changed Ri is equal to rho L by A to L by sigma Ia. Okay, then I am substituting the sigma back into this equation. So Ri is equal to L. What is L? L is given as 1 centimeter long. So this centimeter is to be converted into meter. So into 10 power minus 2 divided by, then sigma I is 2.32 I have got. Then area. So area is nothing but product of width and thickness. So 1 millimeter into 1 millimeter, which means 1 into 10 power minus 6. Okay. So I will get the final expression to be 4310 ohms. So this is the value of resistance. So write down everything. We will go to the next problem. Now read the problem. A semiconducting crystal 12 mm long, 5 mm wide and 1 mm thick has a magnetic flux density of 0.5 Weber per meter square applied from front to back perpendicular to Rogers faces. When a current of 20 milliampere flows lengthwise through the specimen, the voltage measured across its width is found to be 37 microvolt. What is the Hall coefficient of the semiconductor? So you know the semiconducting material, how the specimen is placed in the Hall effect. No, that has to come to mind. See, you are drawing like this. You know, current is sent in the along the x-axis. Then through z-axis, magnetic field is there. Along y-axis, you get the Hall voltage. That is our setup. And this is breadth and thickness. Okay, now come back to the problem. What is given? Let us first write. Length is given as 12 mm. So mm is not SI unit. It has to be converted. So 12 into 10 power minus 3. Then width is given 5 mm, 5 into 10 power minus 3 meter. Then thickness is given 1 mm, that is equal to 1 into 10 power minus 3 meter. Then current is 20 milliampere, so 20 into 10 power minus 3 amperes. Then what else is given? 37 microvolts is given. What is this? Hall voltage. Yeah, so VH is equal to 37 microvolt. So 37 into 10 power minus 6. Then what is given? B, that is magnetic flux density is given 0.5 Weber per meter square. So all these are only given. So what is asked in the problem is Hall coefficient, that is RH. So in the experimental verification of Hall effect, we have written this equation RH is equal to VHB divided by IH into capital B. So this capital B represents what? Flux density, small b represents the breadth. Okay, so VH is given in the problem, substitute. Small b is given as 5 mm, substitute. Then IX is given, that is I is given by this picture. You can understand we are assuming it along x-axis only. So Ix is 20 milliamperes into 10 power minus 3. Then capital B is 0.5. So the final answer is 1.85 into 10 power minus 5 coulomb per meter. Coulomb power 1 and a meter cube. So when you substitute all these terms in the calculator, no, you should not handle this power terms separately and the whole numbers separately. You should know to feed all the data in the way it is written in this equation. Okay, so without mistakes, if you handle the calculator, you will get the correct answer. So the thing is, you have to know how to handle the calculator perfectly. So for which you need practice. So keep practicing more problems, you will be able to do it well. Okay, this is very simple problem. Like this, you can see, refer to other books or our own book to do assignment problems. Okay, digital content is there, you can refer there, lot of problems will be given, so you can solve those problems also. So we'll go to the next problem now. So let us read the problem now. The energy gap of silicon is 1.1 electron volt. Its electron and hole mobilities at room temperature are 0.48 and 0.013 meter square volt power minus 1 second power minus 1. Evaluate its conductivity. Another standard type of problems. So if Eg is given, that is 1.1 electron volt. So you have to convert this. Electron volt does not come under SI unit. Only joules is the required unit. So 1.1 into 1.6 into 10 power minus 19. So you get 1.76 into 10 power minus 19 joules. Then what else is given? Mu E and mu H are given. So what is asked in the problem? Evaluate its conductivity. So sigma I, direct problem, no? So Ni into E into mu E into mu H plus mu H. Now what is not given? Yes, Ni is not given in the problem. So you have to write Ni expression in terms of Eg. Okay, so 2 into 2 pi m star kBt divided by h square whole power 3 by 2 exponential minus Eg by 2 kBt. Then 2 in, so substitute all the values because m is 9.11 into 10 power minus 31. Kb, you know, it is 1.38 into 10 power minus 23. Then temperature is given, at room temperature is given, so it is 300 Kelvin. See, room temperature is given, so it is 300 Kelvin. Then H is also a constant value. Now coming to next term, exponential minus Eg. Eg just now you have converted into joules. So write that here. Then 2 kBt, everything is known. So find out Ni first. So the answer is 1.487 into 10 power 16 per meter cube. Now substitute this Ni into this equation. Okay. So Ni, E, mu H. Now everything is known to me. So find out the answer. Okay. So in order to save time, I have just written everything before. Okay. So write down everything. You can stop the video, note down everything, replay it, use the calculator. Okay. Do the problem, then check the answer. So you can do everything. That is the comfort of the video lecture. Okay. Now we'll go to the next problem. Now read this question. The resistivity of an intrinsic semiconductor is 4.5 ohm meter at 20 degrees C and 20 ohm meter at 32 degrees C. Find the energy gap in electron volts. One very often repeated model of question. Okay, so you are given two temperatures and two values of resistivity and you are asked to find out energy gap Eg. Okay, so I am naming the given resistivity as ρ1 and ρ2, then given temperature as T1 and T2. I am converting the temperature into Kelvin. Then I know the formula for sigma. Sigma is equal to C exponential minus Eg by 2 kBT. So 1 by sigma is ρ. So when I reciprocate it, this minus Eg will become plus Eg. Okay, so exponential Eg by 2 kBT. Similarly, here C is there, no, 1 by C, some constant is going to come. So I am just converting, I am considering that as capital D. Then this is done for 1. So 1, that is first temperature. So which means it is ρ1. Do it same for second temperature also, which is called ρ2. So ρ2 is equal to capital D exponential Eg by 2 kB T2. Now what I want is Eg. Eg is present inside the exponential. Eg will not change so long as I am not changing the material. I am only changing the temperature and because of that resistivity also changes. Okay, but material is not changed, so Eg will not change. So you should not give Eg1, Eg2. Okay, that mistake should not be done. Now take the ratio ρ1 by ρ2. So divide it, the constant gets cancelled. So you get exponential. Eg by 2 kB is constant. You take it outside, common, take it outside. So 1 by T1 minus 1 by T2. So substitute all these values. Then rewrite the expression for Eg by taking ln on both sides. So you get the final answer as 0.998 electron volt. You will get it in joules and you have to convert that into electron volts by dividing by 1.6 into 10 power minus 19. Then you will get Eg is equal to 0.998 electron volts. This is one most frequently repeated end semester exam question. Okay. Thank you, students. Solve more problems. Okay. So with this, I am completing this video. Thank you, students.